On each hand, that's even better. But go ahead and stick your arms out. Are you kidding me? Times your angular or rotational velocity. What if I get this thing? You kidding me? If I say...
Pardon the interruption, this is just a test of the pieces in Stowe High School. Thank you.
Hi there, welcome to my lesson on angular momentum. I have a couple of weights, 5-pound weights, because that's all I can lift. And I have a rotating platform here. I'm gonna make a little bit of a combination of these two things. In fact, before I even get to the rotating platform, let me go ahead and do something with you. Go along with me here, try this at home. Go ahead and put your arms out. If you have something to put in your hands, like some small weights, better yet. And I want you, with your arms out, I want you to rotate at the waist, lock in your torso with your arms, and rotate like this. And do it as fast as you can. Doesn't have to be big, just feel what it's like to do it as fast as you can. It's pretty hard. Now bring your arms in close and even cross them. Now do it as fast as you can. This is pretty easy. So what's the difference? Well, it's rotational inertia, or otherwise known as moment of inertia. Regular linear inertia just depends on mass. But rotational inertia depends not just on the amount of mass, but also where the mass is. So if you bring the mass farther from the axis of rotation, then the inertia will increase. When you bring that mass in close to the center of the rotating axis, then the rotational inertia will decrease. Linear momentum is mass times velocity. More mass, more momentum, more velocity, more momentum. And in a collision or any sort of interaction, as long as there's no outside forces, the momentum is conserved. Well, we're going to have a very similar situation here where the angular momentum is going to be conserved. Except rather than it being mass times velocity, it's now rotational inertia, which is essentially the angular equivalent of mass, times the angular velocity, the angular equivalent of velocity. Angular velocity is represented by how quickly you're rotating. So if I rotate faster, then clearly I have a faster rotational or angular velocity. Don't confuse that with a linear or tangential velocity. That might be represented by like the tip of my finger. Okay, my fingernail is moving at a certain velocity along its path, along the circumference of the circle. Okay, so if I go around about once per second, the velocity of my fingertip is, measured in meters per second along its path because it travels that circumference distance. Versus my angular velocity is effectively how quickly I am rotating around in a circle. If I'm going around once per second, then it doesn't matter what part of me you're looking at. It's the whole thing, going around once per second. So if angular momentum is the rotational inertia times the angular velocity, what's different about linear momentum versus angular momentum is I can change my angular rotational inertia. So watch. I'm going to go from a large rotational inertia to a small rotational inertia, right? Large to small. And here we go. I have angular momentum. It is going to be conserved because of the friction-free environment that I'm in, mostly. Let's get going real good. And I'm going to make it a small rotational inertia. Ready? I feel like there's some friction there. Hold on, let's try that one more time. I'm busy already. I haven't even done anything. Ready? Set. Okay, now I'm dizzy. Oh crap. Ooh, Billy. All right, one more, just for good measure.
If you're gonna spew into this.
I'm not gonna fall over. I'm not gonna fall over. Okay. Let's do another one. Hey, I have this wheel. It's a really big wheel, actually. It's a 29-inch wheel. I chose that because the larger it is, the more rotational inertia. Let me go ahead and step on this rotating platform here, along with the wheel. Clearly, as a system, an interacting system, we have an angular momentum of 0. So if I give it momentum, it gives me the opposite momentum. I'm going to give it momentum in this direction. This direction, viewed from above, would be counterclockwise, but we will say that the momentum, or the angular velocity direction, is up. Why up? Right hand rule, not left hand rule, right hand rule. So as I sweep my fingers and close my hand, it is in the direction of the spokes moving, and my thumb will point up. That doesn't mean that things actually moving up. It's just that if you're looking from above, it's counterclockwise. If you're looking from below, it's clockwise. And depending on our orientation, we might not agree on its direction. The wheel has a momentum of 0. I have a momentum of 0, at least an angular momentum of 0. And if I give it a positive direction, I'm going to call up to be positive. I give it a positive direction momentum, then it's going to give me a negative. I'm going to spin this way. I'm going to spin it this way. I'm going to spin the other way. So watch that carefully. Right? Equal and opposite reactions, also true of rotating bodies. So now, what if I get this thing moving, and now I step on? So as a system, we have angular momentum that is in the up direction, and then I'm going to remove that momentum that it has. What's going to happen to me? Ooh, that's fun. Wait, what if we both go in that direction? Oh, Nelly! So, angular momentum. By the way, how about this for dirt bikers? For dirt bikers that go off of a jump. They have a wheel that's spinning in this direction. In fact, they have 2 of them. What if, oh no, I'm about to land on my back. Can they do anything midair? What if I'm about to face plant? Is there anything I can do? Hit the gas, go the other way. Hit the brakes, pitch down, hit the gas, pitch the other way. So, yeah, it's a good little bit of fun there. In fact, let's do that one more time. That there is called gyroscopic precession. There's torque that is applied by gravity, right? Gravity's pushing down, it wants to keep rotating this way, but torque is being applied, so the system must rotate the other way to balance. And one more time this way. Oh, let's get this thing really going, just for one good measure, and then we'll say bye. Ready? Oh, it's hard to do. By the way, if you ever get a chance to play with one of these, just simply do this. It's really weird. Really very strange feeling. That's it. You guys have a good one. See you next time.